Hi guys, and welcome to the next in the series of acidic environment videos. This one is on the salts of weak acids and bases. And just excuse any background noise, there's a little bit of wind whistling around today, so hopefully that won't be too distracting. So what we want to do today, now we understand a little bit about conjugate pairs, conjugate acid-base pairs, we can start to analyze the salts that form from different, not only that are produced in different types of reactions, but also from neutralization, and see if we can classify those in some way. So the first one we want to look at is sodium chloride. So sodium chloride is NaCl, and when this goes into water, it will dissociate into sodium ions and chloride ions. Now what we want to do is we want to try and have a look at how the chlorine is likely to react with water molecules. So if the chlorine was to interact with a water molecule, then the chlorine is going to, in this case, act as a base. It can't act as an acid because it doesn't have a proton to give up, but it can act as a base. If it acts as a base, it's going to accept a proton, forming this species and OH- ions. Now, this should increase the concentration of the OH- ions, but only if the reaction is going to proceed in this direction. And the problem is that we have HCl, which we know is hydrochloric acid, a very strong acid. And therefore, this reaction is going to go this way, not this way. That's not going to work. As a consequence, sodium chloride and indeed other chloride salts have a pH around about 7. There's no significant interaction between the chloride ion and the water molecules, and so therefore the pH of the solution remains around 7. This, however, is not the case for ammonium salts. Ammonium salts are NH4+, okay? Ammonium chloride, ammonium nitrate, whatever. So ammonium something. So perhaps if we put over here some examples of ammonium salts, maybe NH4Cl or NH4NO3 nitrate. Okay, now we already discussed what happens with the chloride. So we know that if we're looking at ammonium chloride, for example, we know the chloride's not going to affect the pH of the solution in any way. So let's see what happens with the ammonium ion. Well, what the ammonium ion does is it is going to react with the water, and when it does that, this is going to act as an acid. And if it does that, it's going to donate, okay, to this one, which is going to be in aqueous solution. And it will, because it's donating, it's going to produce the hydronium ion, H3O+, aqueous. Now, of course, the thing we need to check is that we've made sure that everything's balanced. 1 nitrogen, 4 and 2 is 6 hydrogens, 3 and 3 is 6 hydrogens, 1 oxygen, and also an overall 1+ charge. So we've got a balanced equation here. But where does it lie? Well, what we know about ammonia is a weak base. And because ammonia is a weak base, this equilibrium, if you like, is actually going to lie on this side. It's not going to readily ionize and come back to this side. So that means if we start from this, we're actually going to drive the reaction in this direction. What that means is that ammonium salt is actually going to increase the concentration of hydronium ions. They, we've already said, are equivalent to H+ ions, and therefore the pH will actually fall. It will be less than 7. Now we can also apply the same logic to carbonate salts. Okay, here's the carbonate ion, CO3 2-. Okay, so sodium carbonate, calcium carbonate, doesn't matter what the salt is over here, you can put some examples down, Na2CO3. What happens when this dissolves in water? Well, this is going to combine with water, liquid, and I'll put it as an equilibrium because we're going to try and see if we can figure out where it's going. Now, there's no protons in the carbonate ion. So therefore it's going to have to act as a base. If it acts as a base, then the water molecule must be acting as an acid, and therefore it's going to donate. So we're going to get an HCO3 1- ion and an OH- ion. Notice here, again, when we're checking 2 hydrogens, 1, 2 hydrogens, we've got 1 carbon over here, and we've got 3, and 1 is 4, 3 and 1 is 4, and we've also got a 2- charge here, and we've got -1 and -1, which is -2 over here. So again, we're balanced. Now what we've said again is this time we are going to be producing a substance, or we're going to have a salt, which is going to sit in an equilibrium, which is going to lie a little in this direction. The consequence of that is that this becomes the conjugate acid, and of course the hydroxide is the conjugate base of water. But what that means is that the concentration of the OH- ions is going to increase, and what that does is it will increase our pH, which means that in very general terms, this is a neutral salt, sodium chloride. This one, an ammonium salt, is an acidic salt, and the carbonate is a basic salt. And this is basically the test that you will use in order to determine whether or not you think something is neutral, acidic, or basic. And this again, I guess, leads us into another one of these species that can do either, and that we call antiprotism. And the bicarbonate ion is a good one to pick because the bicarbonate ion can do anything, and if we put it with water we can kind of get a sense of what it will do. And I'm going to actually have an equilibrium here, which I'm going to write twice. And it's probably a good idea while you're watching this to see if you can identify the conjugate pairs. So in the first one, I'm going to make the bicarbonate ion act as an acid. So if it's acting as an acid, it's going to donate a proton, which means it's going to go down by 1 hydrogen and 1 charge, and the water molecule is going to have to go up by 1 hydrogen and 1 charge. Likewise, in the second of these equations, so this is the first one, this is the second one, this one we're going to have this acting as a base. Notice in each case the water molecule has actually taken the alternate role. So if this is acting as a base, then we've got it accepting a proton, and the water molecule this time is the one that's donating. Okay, both of these obviously will be aqueous solutions, aqueous, aqueous, aqueous. You know, we have to be careful with these subscripts because we are going to get in trouble with them if we don't keep putting them in. Okay, it's assumed most of the time, of course, that ionic forms are going to be in aqueous solution, but occasionally they can be molten salts, so then they would be liquid. So this removes any ambiguity, which we always like to remove. And now you can see that the bicarbonate ion can act as both an acid and as a base, just through the Bronsted-Lowry definition of being a proton donor or a proton acceptor. And so therefore, we would have to know something about the relative equilibrium between these two positions to know which of these two is more likely to occur when the species is in water. Is this more likely to be a substance which is going to lower the pH of water and therefore produce H+ ions, or is it going to increase the pH by releasing OH- ions? So I'm going to see who's watching this and who asks me that question in the next day or so. But for now, I'm going to ask you a question. And this one came out of the 2010 HSC, and it was question 21. For 3 marks, you were told that a 0.001 molar solution of hydrochloric acid and a 0.056 moles per litre solution of ethanoic acid have the same pH. Why do they have the same pH? Well, we know that the calculation of pH is based on the negative log, the concentration of hydrogen ions. So therefore, what we should do is put the concentration. We know, for example, hydrochloric acid is a strong acid, and therefore all of it will ionize, it will completely ionize, and therefore we can assume that the pH is going to be equal to minus the log of the concentration of H+, which is minus the log of the concentration of, 0.001, and therefore the pH is going to be equal to 3. Check it out in your calculator. So we know that one's right, and it also fits with that. But clearly, the ethanoic acid, even though it's a monoprotic acid, so it's only going to monoprotic acid is only going to liberate one H+ ion per molecule. It's got a much higher concentration. So therefore, if it's also has a pH of 3, then that must be because this one, the ethanoic acid, does not fully ionize. Okay? The equilibrium between the acid, and I'm going to deliberately leave the subscripts off at the moment because we just want to have a quick look, is going to liberate the hydronium ion and leave us with a CH3COO- ion. Okay? But this one doesn't go fully in this direction. It doesn't go to completion. So we still have some of this species left, which means the 0.056 moles per litre that we have of here do not translate into 0.5056 moles of this. And therefore, the pH is lower than it would otherwise be. Thanks for listening.